just in terms of format for this, feel free to ask questions throughout the middle of the presentation. And if you do, just raise your hand and someone will come to you with a microphone. Okay,
cool. Thanks. So thanks for the introduction, Herb, and for the invite. I'm glad I can be here. So this is going to be kind of informal and open. This slide deck is actually far longer than most people want to sit through. It has a lot of technical details. It's probably only you would only want to know if you wanted to actually implement a deep learning algorithm to work on a problem of interest to you. But yes, that's right. So what I gather from Herb is that a lot of you guys have read some deep learning papers, maybe had some discussions, seen some deep learning talks. Maybe some of you work with machine learning in industry, want a little bit more technical grit, so that if you actually wanted to implement something, you'd have a place to start. So a lot of that is sort of the goal of the stuff I'm going to talk about. But if it looks like things aren't making sense, feel free to raise your hand and we'll slow down. If it's way too easy, then hopefully everyone can aid me on and we'll go faster. And so we'll just kind of do this informally and discuss it along the way. No, I've already got one hand full. Can everybody hear me okay in the back? Okay. So first I want to sort of motivate why we do deep learning at all by talking a bit about what do we want machine learning to do generally. So the basic idea behind machine learning is that if I give you an image, I give you some piece of data, I want to learn to make some kind of prediction. For example, if I give you this image, one thing I might try to do is train a computer to be able to predict that this is a cat, or maybe tell me that it's not a cat. And even though I'm going to talk a lot about problems that look like this for the sake of sort of a tutorial, you can apply these same ideas, the same basic framework to solve all kinds of things. So for example, if I wanted to, I could train a machine learning system to decide whether a particular box contains a bicyclist, and if I sweep this over an image, I can help you find the bicyclist and actually frame it. So this is really useful for lots of different applications. You can do the same sorts of things if you want to do, say, image segmentation, where I want to take an image and I want to outline the objects, for example. So even though I'm going to talk about a handful of applications, just keep in mind that there are sort of different tricks and so on to shoehorn these things into other applications. So how is it that we actually do machine learning? And so there's a sort of classic pipeline that covers a huge, huge fraction of the way machine learning is actually done in practice. So for example, if I give you a bunch of data, like images of cats, what we usually have is some feature extraction system. It's a sort of hand-coded piece of software that tries to transform this data into a new representation that I think makes it better for machine learning. And we'll talk about why that's important in a minute. And once we've got this, then we're going to put it into some machine learning algorithm, some off-the-shelf system usually, and try to train it to make a prediction about whether this is a cat, and hopefully be able to answer this question by the end. So sometimes the way that we try to build this thing to make the system work the best is to keep encoding increasingly high levels of abstraction. So you could think about a good way to represent an image to make decision making easier would be to first detect edges or say texture in the image, and then maybe try to find parts based on the low-level edges, and then maybe put the parts together to find objects before trying to decide what that object is. And in practice, the way that we end up building these things is to put all of our prior knowledge and experience about the world and try to wire it into this system. Like, how is it that images work? How do we remove shadows and blemishes from the image that might confuse our algorithms? So deep learning is sort of based on this observation that when we build representations in practice, when we try to take an image and change its form so that machine learning works well, what we try to do is construct several layers of increasingly high-level features. We try to detect higher and higher level concepts so that our classifier at the very end, our machine learning algorithm, has a really easy decision to make. And just this basic picture sort of covers the high-level thing that we would like deep learning to do for us. We'd like it to build these increasingly high-level representations in order to make machine learning software that works better. So the question then is, why do we actually want deep learning? What is it that's so bad about this pipeline with hand engineering? So there's some intuition for why we might want to build deep things. One is that if you think about how is it that you decide that something is a cat, it's pretty clear that this evolved through several stages of processing. It's very difficult to start from the pixels of an image, just raw pixels, and immediately say that this is a cat. We should just intuitively feel that the decision is much more complicated than that. So having several stages of processing is often really useful. Second, just from years of experience of playing with computer vision systems, we know that we tend to build several stages of processing anyway. It's very rare that you find an algorithm that can recognize cats, for example, or human faces that just involves one quick decision. We know that we tend to build up several layers of these things before we use them. And finally, it turns out that the deep learning algorithms, and many of these machine learning algorithms in general, actually scale really well with the amount of data that we have and the amount of computing power that we have. So this is not a motivator in itself, but sort of a side bonus of these kinds of algorithms. Hopefully, maybe say a little bit later about why this works as well as it does. So raise your hand if you've heard of neural networks. You've worked with neural networks before. Okay, pretty much everyone. So many years ago, there's a lot of research in neural networks. And maybe you've seen pictures of neural networks, and there's sort of these layered structures. And that is basically a deep representation. There's a lot of work on how to train these things to do different tasks. So a good question is that deep learning? Does that solve the problem? And I'll say yes, that is actually a form of deep learning. But a good question then is, have we been here before? Is this all just stuff that we should have known ahead of time? And there are really two answers to this, both of which are basically correct. So on the one hand, a lot of the stuff that you're going to see, you can go back in the literature and you're going to find papers about these exact same ideas that are 20 years old or even older. And a lot of this stuff, if you do machine learning in your job today, you'll find that you can actually take a lot of things that you know from machine learning, the ways that you debug algorithms, and you can just reapply them to deep learning. In many ways, there are going to be things that just haven't changed. Neural networks haven't changed so much, and the strategies that we use to debug them have not changed that much. So the other thing, though, is that some things about this field really have changed quite a lot in 20 years. In particular, we have vastly faster computers, which makes prototyping and debugging much faster. But critically, we also have far, far more data than we used to have. So if you can build a very expressive, complex decision-making system, it turns out you need a lot of data in order to tune it and make it work well. So having all of that data available, because we have things like Google and ImageNet and Flickr and so forth, that actually helps quite a bit. But on top of that, we also have some more like algorithmic innovations that have happened in the last maybe 5 to 10 years. In particular, many of you may have heard of something called unsupervised pre-training, which is a pretty cool trick that is in many ways responsible for this resurgence in neural networks research. And it turns out that maybe you don't really need this thing. We can talk about it later if people want to stick around and are interested in. But I'm going to tell you a little bit about sort of how to get away without using this. So even though you may have heard of this before, it's actually not necessarily needed. And finally, one other thing that we've built up over the years is we have tons of empirical evidence now for what works and what does not. Because every grad student has a really fast computer on their desk with a graphics card. They can try lots and lots and lots of things on a very sizable, practical problem and figure out what things work and what things don't. And so you can find papers out there that have really done the hard work, the legwork of implementing many different algorithms and figuring out which one works the best. Finally, one of the last things that we love so much about deep learning now is this having real impact. So we are now at a point where I think we can comfortably say that deep learning systems are state-of-the-art in many different applications. And this gives us actually a lot of hope that there are some new applications out there that maybe we weren't thinking about because they seem too hard, where maybe deep learning can help. So for example, in image recognition, really tough problem is telling what is actually pictured here. So maybe like 5 years ago, I would have said that deciding that this was a leopard was an unbelievably hard problem that I did not expect to be solved in 5 years. And yet, there are deep learning systems out there now that can actually competently recognize that this is a leopard. And in fact, if you look at the other sort of top recommendations of this deep learning algorithm, they're also very plausible. Is it a jaguar, a cheetah, probably not a snow leopard or an Egyptian cat? But all of those are actually quite plausible considering the content of the image. So anyway, even though I'm going to talk about image recognition and vision applications for sort of the rest of this talk, it's worth pointing out that speech recognition is another huge area where deep learning is having a big impact. So right now, if you use, for instance, an Android phone, chances are you're using a deep learning algorithm. And also in places like text, where we really have gobs and gobs of data, deep learning is having a big impact for understanding language, being able to help with applications there. So that's sort of the rough overview. How does machine learning work? What is deep learning, and why do we think it's cool? So now we're going to kind of jump into sort of a crash course on machine learning. So raise your hand if you've taken like a machine learning class or you've implemented a machine learning algorithm. Wow, pretty much everybody. That's great. Okay, so this may seem like old hat for a lot of you, especially if you do this every day. And for those that haven't taken one, then we'll try to fill in the blanks as we go here. So the basic framework that we're going to start with is called supervised learning. So in supervised learning, the idea is that I'm going to give you a bunch of examples, and I'm going to tell you what they are. So for example, I'm going to give you this image of a cat, and I'm going to represent the cat as a vector, xi, that has all of the pixel intensities, the brightness of each pixel in the image. And then your job is to somehow invent or find some function, f of x, that can predict whether this is a cat or not. And the fact that this is a cat is represented by the label y. And when I train this algorithm, I'm going to give you that label. And it's your job to find some function that's really good at predicting the correct label on the examples you've seen. So hopefully, if we have a good machine learning algorithm that finds f of x that gets the right answer most of the time on our examples, that will usually mean that when we have some new example where we don't know the label, the prediction will also be good there. So I'm going to give you a sort of a quick explanation of a simple binary classification algorithm. This is a real machine learning algorithm you can actually use to do a whole bunch of different things, called logistic regression. And what logistic regression tries to do is learn to classify between two different classes, a 0 class and a 1 class, or a negative and a positive class. So the way that we're going to implement this algorithm is first we have to choose some way to represent f of x on the computer. So I said previously we want to find the best f of x, the best function to predict these labels. But in this case, I'm going to restrict myself to only looking at functions that take this particular form. So I'm going to start with some parameters theta that are tunable. I get to choose those values. And this function just takes theta transpose x, a dot product. And then once I've taken that linear function of x, I'm going to pipe it through this function represented by sigma, which is just a fixed, hardwired, nonlinear function. And there's actually a reason we use this particular function, but you can just think of it as a squashing function. All it does is it takes this linear function of x and it maps it into the range 0 to 1. And the idea is that if I map it into the range 0 to 1, I can think of it like a probability. Yeah. So our job now is actually going to be to minimize an objective function. I'm not going to go through where this thing comes from, but just take my word for it that this function of theta tells me how well f fits my data set. It tells me how well f is able to predict the labels y on the training examples that I've collected. And in particular, you can think of f of x as being the probability that y is 1, like the probability that a particular image is a cat. And 1 minus f of x is like the probability that y is 0, the probability that this is not a cat. And then this thing wrapped around it, which we call a loss function or an objective function, this thing tells me how good is this particular choice of f of x at making predictions on my training data. So does everybody kind of follow? Some nods? Yes? Okay. Good. So once we've done that, I said our goal is to find the best f of x. We want to find the function that predicts the labels as well as possible. And we do that by minimizing this loss function L of theta. So we want to find the theta that minimizes this thing. So how do we actually do that? It turns out you can go on the web, actually, and you can download all kinds of optimizers. You can use MATLAB to do this. But for various reasons, I want to give you a very simple off-the-shelf algorithm that, in fact, we still use everywhere in practice. It's called gradient descent. So the basic idea is that if I can compute the gradient of this function with respect to theta, which is just the vector of all the derivatives of L with respect to the elements of theta, then if you remember from your high school or college calculus class, the gradient is the vector that points uphill. It's the steepest direction of this function. So if I move in the direction of the negative gradient, that's like moving downhill as quickly as possible. So what we can do is we can compute the gradient of this loss function with respect to theta, and it turns out to be this thing. So if you take the equation I gave you on the last couple of slides here, compute the gradient, you actually get this expression. And this is actually very intuitive. It says, assuming that, let's say that just x is positive here, we have positive valued pixels, it basically says that whenever my label is positive, but f of x is too small, meaning I estimated a low probability, but that the real label is 1, then what it's going to do is it's actually going to increase that coefficient in theta. It's going to say this particular feature in x is actually associated with a positive, with the example being positive. And if y is 0, but f of x is very large, then it's going to make the opposite adjustment. It's going to decrease theta. So you can see how this algorithm kind of intuitively learn which of the elements in x tend to be cats, and which of the elements in x tend to be associated with things that are not cats. And once we've got this gradient, we're just going to take whatever our current guess is for theta that represents our function, and then we're going to move downhill a little bit. And then we're going to do the whole thing over again. And it turns out if you iterate this for a while, you'll eventually get to an optimum that minimizes this function. And in fact, even though I wrote it here, this is a sum over the whole data set, over all the examples that I have. If you just get rid of this summation here and only do this for one example, this is an algorithm called stochastic gradient descent, which is a really fancy name. But it turns out we use this all the time in practice. So if you go to train a neural network, you're going to see this algorithm all over the place. So the question that you might ask is this actually enough? It seems like a pretty naive algorithm. I just gave you this function that says how good f is, and all you're doing is going downhill in the steepest direction possible. And it turns out that actually is enough in this case. So there's a particular property of that quality function I gave you, the loss function, which is that it's convex. It's a bowl shape. What that means is that if I keep going downhill, that eventually I'll get down to the bottom of the bowl, and this algorithm will actually converge, provided I don't go too quickly, and it'll go to the very bottom of the bowl, which is the minimum. So in fact, if you set this up correctly, you can always find the best function that has that form, no matter what your data set looks like. So this is pretty neat. And you can actually do some fairly non-trivial things with this. In particular, if you download, for example, the MNIST digits data set, and you try to classify digits like 0s and 1s, and I just feed this into the algorithm that I just explained to you, you can actually classify these things perfectly. You can actually get a classifier that distinguishes between 0s and 1s all by itself without having to be told. But if you look at these a little bit, you can kind of see that it's not as hard as you might think. And the reason that this turns out to be a fairly easy problem is because some of these pixels are actually very highly informative. For example, if I look at a pixel in the middle, when it's a 0, the pixel tends not to be turned on, and when it's a 1, the pixel does tend to be turned on. So it turns out that this classifier is able to figure out that there are some pixels in there to look at that are very strongly correlated with whether it's a 1 or a 0. But this algorithm, logistic regression, is sort of the basis for what I'm going to talk about next. So unfortunately, this actually fails for even slightly harder problems. So here's a much harder one, though. For example, if I give you an image that looks like this, can you classify this thing as a coffee mug or not a coffee mug? It turns out if you take the algorithm that I just described and apply it to images that look like this, with yes-no labels of whether it's a coffee mug, it will fail completely. So it's worth asking then, what's the difference here? Why is this so hard? And the basic problem is that even though you and I see a coffee mug, it's pretty trivial for a human, the computer is seeing this. It's just seeing this big grid of numbers, right, all stretched out into a vector. And it's very unclear why these pixels, or how these pixels could be used in some simple way through this linear function to decide if this is a coffee mug or not. It's a very complex decision, but you saw we were using this very simple nonlinear function to make an estimate of whether it's a mug or not. So to see sort of at a cartoon level what the problem is here, I want to sort of take the extreme case. So instead of thinking about this coffee mug as represented by like 1,000 intensities, let's just represent it using only 2. So we're just going to take this coffee mug, and instead of trying to think about the whole thing, we're just going to represent that entire image with only 2 numbers. And those 2 numbers are going to be the intensities of the pixels at these 2 locations. So for instance, in this image, maybe this corresponds to a point, coordinates with 72 and 160, corresponding to the brightness in this image. And if I create a 2-dimensional scatter plot here, then I can plunk down a point there that represents this coffee mug. And I can take another coffee mug from my data set, and I can plunk it down over here. And I can also do these things for the 0 class, things that are not coffee mugs, over here. And if I do this for a whole bunch of points, maybe I get an image that looks like that. And now it seems like, gosh, if I put this into a machine learning algorithm, what am I really expecting to happen? If I ask you for a new point somewhere in this image, is this a coffee mug? It's not surprising at all that the machine learning algorithm has no hope. There's no way you can expect to decide if this is a coffee mug. So this is really a key problem in machine learning, is the fact that these 2 pixels are a terrible way to represent an image, let alone coffee mugs. But if I just wanted to describe the whole image, this would be a very bad way to do it. On the other hand, let's suppose that I could just give you, someone, a very talented engineer comes by and gives you 2 detectors. And the detectors will tell you, sort of at a soft level, whether you have something that looks like a cylinder in the image, and whether you have something that looks like a handle in the image. And it might be 1 if it's really confident, it might be 0 if it thinks it's not there, but it could also be some value in between. So if I do the same thing now for all of my data points, it wouldn't be surprising to see that all your coffee mugs are up in this corner, because the coffee mugs are amongst the only things in the world we see that are cylindrical with handles on them, especially around our lab. And then all the things that are not coffee mugs, that are just like coffee cups or pieces of tables, carpet, chairs, and so on, they're all down in this corner. Now if we apply our machine learning algorithm, just like logistic regression that I already showed you, now it's an easy problem. In fact, if it really looked like this in 2D, logistic regression would solve this problem just fine. So the high-level picture here is that the representation of our images matters a lot. We have this algorithm, logistic regression, that's not very powerful, but if we can change the representation of our image to look more like this, then a very simple algorithm like logistic regression will work just fine. So that's really the basic idea behind that system I talked about earlier. This is why we bother to create these feature extraction systems. What we're trying to do is somehow engineer a transformation, some way to re-represent that coffee mug by finding handles and cylinders and what have you, so that our machine learning algorithm at the very end can do really well. So this is the sort of more detailed picture of why we actually go through that big pipeline. So So we still have most people? Raise your hand if this is making sense. Too easy. Guys.
I just had one
Yeah.
question. The training set, somebody has to manually go through and classify each upfront? Or
Yep.
is it
So this is actually a great point. So the kind of machine learning that I'm describing to you right now, called supervised learning, assumes that someone has sat down and told you that these are coffee mugs and these are not coffee mugs. So if you wanted to solve something like recognizing 1,000 different object categories, that is a huge, huge amount of labor.
Yeah.
And 5 or 10 years ago, you would not have been able to find a very good data set that looked like that. That is different now. Today, you can go to imagenet.org, and you'll see there are about 15 million labeled images.
some people have done those?
That's right. You probably all heard of Amazon Mechanical Turk? Yeah, so great service. Because it turns out for a few cents, you can send some images up, and people will label these things for you. So this is a huge, huge boon to machine learning, and especially to deep learning, which really loves to have lots of data.
Isn't this the problem? You mentioned earlier voice recognition on Android, for example.
Mm-hmm.
So Google's Reco engine, which is neural net based. And they have to train every word. And so one of the problems of that system is that it knows things that are said in highly dense populated areas where Google is selling lots of technology, but doesn't understand how to represent words or last names of people from regions where they're, and
Yep. So if you don't have labeled data for the thing that you're trying to predict, you can end up sort of lost in the wilderness. Pretty interesting, actually. This is one hypothesis for why speech has done so well of late. People working on the speech problem worked really hard, knew that having lots of labeled data was important for doing different kinds of analysis, and built these amazing annotated, transcripted databases. And so when deep learning came along and machine learning came along to gobble up all that data, sort of a ready-made problem for these things to work on.
Isn't there also a problem with these photos perhaps were taken by humans as opposed to just random photographs that, you know, that they might be aligned like people's faces or portraits?
Right. So in something like ImageNet, they'll often put bounding boxes around them. Sometimes there are weird biases in the data that you're looking at. And those are all things that as an engineer or a machine learning practitioner, you actually have to think about. So for instance, if I train you to recognize cats in images, but I always train you on images with really nice lighting, and then I show you some images of cats in really horrible lighting, there's no guarantee that that's going to work. Sometimes it does, sometimes it doesn't. So there's a sort of theoretical assumption that goes into most of these algorithms to prove that they work, and that assumption is usually that whatever you trained on is also what you're going to test on, up to actual random sampling. So that looks like a question in the back.
So are you saying that the feature extraction of, what is a handle, what is a cylinder, is totally unsupervised? So you can extract things, textures, orientations, slopes, gradients?
Right, so in this case, I kind of used these because they're easy to understand. How you would actually build a handle detector, if you don't know how to build a coffee mug detector, is not clear.
Well, I'm saying in an unsupervised sense.
That's right. So here it's assumed that this is hardwired. Someone just gave it to you. They built it by hand.
That's my question.
Yeah.
Is the proposition in deep learning that the feature extraction itself would be largely unsupervised, or do we not know?
So I haven't got that far yet, but it could be either one. One popular way to try to do it is to train it unsupervised, but you don't have to. You can actually train everything from labeled data.
So this assumes you know the features up front, right? I mean,
That's
in the
right.
case of an image, it's simple, but what if it was financial data, time series of
That's
data?
right. Huge problem.
I need to know up front what features would be pertinent to that series.
That's right. So, so this is the sort of classic machine learning picture. And there are whole fields where the whole job is to figure out what are the features that will give us this kind of picture here. So, for example, if you want to solve computer vision problems with machine learning, you really have to be a computer vision expert if you want to use logistic regression. You've got to be able to figure out how to change the image around. So you've heard of the SIFT descriptor. Lots of computer vision practitioners all know the SIFT descriptor, one of the most highly cited papers in computer science, because it just turns out that if you extract these descriptors from your image, it makes your machine learning algorithm work vastly better, which is one of the reasons it's so popular and so clever.
for example, I have 2 algorithms, both working. I tell which one is better.
Right. So the question is, if I have 2 different algorithms, and it looks like both of them are fitting my data, right? They're both optimizing this loss function equally well. How do I know which one I should use? So the way we normally make that decision is we go get some extra data that the algorithms have never seen before, and we test them on that. And we take the one that gets the best test error. So machine learning practitioners, this will be old hat to you, but so far I've talked about a training set that we train our algorithm on. It will turn out that you always do better on the training data than you're ever going to do when you deploy your system. It's actually quite easy to fool yourself that your problem is solved, and then you go test it on new data and it doesn't work at all. So I'm going to kind of gloss over these issues until much later maybe, but basically the way that you end up deciding if you're done is you go and test on data you've never seen before to make sure that your classifier is getting new things right that it's not been trained on. Okay, so this is sort of the sort of picture that we want to achieve, and as we've been talking about here, the way we usually cheat this, the way we fix our algorithm, is we build some function that we usually call phi. You'll see this sort of unintrusively slipped into papers, where they created an algorithm and then they engineer some features to make their algorithm work better. So the main thing about this is that this is completely static. So we said earlier, someone gives me this handle detector or this cylinder detector, and it doesn't change. It's hardwired. I can't change it. So the good question is, where do we get good features? And in practice, for a lot of different fields, especially computer vision, it turns out that we spent a ton of time engineering these things by hand. So as a computer vision expert, one of the things that you're sort of building up is an intuition for how images work. What are the sort of salient characteristics about an image? Which is much easier than something like time series data, where we don't have human intuition. But in these things, we're trying to use our sort of human knowledge about how the world works to come up with what we think is a better way to represent images. For example, one neat idea is to take a bunch of object detectors, even if they don't work very well, and try to represent the image by how likely it is that certain objects are in it. So for example, if I think there are things that look like sailboats in an image, even if it turns out there are actually trees that just kind of look like sailboats, it doesn't actually matter. It turns out that if you just want to know, what are the odds that this is an ocean scene, it turns out that just looking for things that look like trees or look like sailboats, equally good kinds of features. So even if you didn't detect the sailboat or the tree correctly, it turns out these things might be good features for deciding what kind of scene you're looking at anyway. And so the same is true for things like superpixels, where we're trying to cut up regions of the image into blocks that have sort of similar texture, so that instead of processing all these little pixels, instead we're looking at sort of big contiguous regions instead. So this is a pretty cool set of literature. There's a lot of ingenious ideas here, many of which we're still using. But so the sort of MO behind a lot of deep learning is to sort of try to escape this. We know that computer vision is one of the hardest applications out there. It's a huge fraction of what your brain is doing. We really sort of feel like if we're going to engineer all these features by hand, that may be a job that's just never done. So what we'd like to do is use a machine learning algorithm to do this for us. So in the last slide, I sort of said there's this function phi of x, like maybe your cylinder detectors, that's going to try to come up with a new representation of your images to make your machine learning algorithm work better. So what we're going to do is take logistic regression, and we're just going to extend it just a little bit here. So before, remember that I had this function sigma, this squashing function, followed by a linear function of x. But now I don't have x anymore. I've squashed another sigma or sigmoid function in there of w times x, where w is actually a matrix. So this is the same thing as before. This outer function is the same as I had in my binary classification algorithm. But this inner part is where I would normally have my feature function. Normally I'd put my features in here. But now I actually have a tunable function where each element in this vector corresponds to one feature. And then the thing to take home about this representation here is that it's the same picture as if I had just stuck phi of x in here and it were fixed. but now I have these parameters W, all these parameter vectors. And if I tune W, I can get these features to represent different kinds of things. And intuitively, if I take W1 times X, that'll be very large when X and W1 look very similar when they point the same direction. And thus this feature will be big whenever X looks like W1. So you could think of W1 as being like a little arc in an image. And whenever I see another arc that overlaps with that thing very closely, then this feature will have a very large value. And if it's some other pattern, then it'll have a very low value. But the actual pattern that I'm looking for could be anything, and it's determined by what these parameters get set to. So to do supervised learning for two classes, just zeros and ones, or mugs, not mugs, cats, not cats, what we want to do is extend our learning algorithm to not just tune theta, but now we're also going to tune W, which represents all of our features. So I can write down the exact same loss function as before, the same objective, where if I minimize this over theta and W, nothing has really changed in terms of what this means. This still says that F fits my data really well. The only thing that I've changed is that I've got some more freedom here. I can pick W now to represent features down inside of F. But as far as what this algorithm is attempting to accomplish, it's the exact same thing. It's going to try to find a way to have a large value of F when it's a coffee mug, or a small value of F when it's not a coffee mug.
What
Yes.
kind of distribution you use? Gaussian distribution?
To initialize it, or? Yeah, so normally when we start our optimization process, we have to set all of these things to random values. We've got to give it an initial guess. And actually doing that properly is really important. I actually have a slide later for those interested on how to do this. But usually something like setting it to Gaussian random values, rescaled, is something reasonable to do.
So if W is a matrix, right?
Yes.
Okay.
So the capital W here is a matrix. The little w's are vectors, or row vectors, rather. So in particular, when you see W times X, that's going to be a vector itself. So basically, this is the exact same thing as logistic regression. Oh, yeah.
So the plus in the cost function should be minus, or should be plus?
You mean this one?
Yeah.
So there should be big parentheses here. So this minus kind of goes all the way through.
Thank you.
Yeah. So this is basically the same thing as logistic regression, the same objective, except that now we changed the way we represent our function. We have more functions to choose from in order to fit our data. And the main way to look at this is that I now have layers. I have these modules that are nested inside each other in order to make decisions. I can make decisions in several steps now. So you can break this out. You can think of this as having two different pieces strung together. So I can think of X as going into this first function and getting multiplied by W. It's just a linear function. And then followed by this sigmoid nonlinearity, this S-shaped curve. And then taking that and just calling it an intermediate value, save it into the variable h. And you can think of these things as being your features, just like you computed features from some detector that someone gave you. And then we're going to take those features and we're going to stick them back into logistic regression. So right here is just your little logistic regression system that you built earlier in the talk. So this is really just kind of an ugly way of sort of composing multiple modules into one big function. And when we go to train this, when we go to minimize this objective function, what we're trying to do is say, find me the best pipeline that looks like this. Find me the best machine that has this form so that F always makes good predictions. That's our goal. So now, what I've just told you, the model I've just explained to you, is a neural network. Yeah.
In your previous slide, you state the likelihood or the probability of the feature being present.
So the question is, does H have a meaning in terms of the probability that a feature has been activated? For this particular case, where H is this sort of S-shaped function of Wx, you could interpret it that way. In practice, H is not going to be easy to interpret at all. it could be almost anything. And what you hope for is that your algorithm invents the best choice of H to make the whole thing work. And it may or may not be detecting parts or something that has a nice interpretation.
But it is related to the feature value.
Sorry, H is related to?
The features value?
Right, so I take X. So think of this little box as a machine. X goes in one side. My machine computes W times X and then applies this little squashing function. And the output, I'm going to store it into H. Like H is a place in memory.
So is this something like principal components analysis, wherein those features that you're coming up with are not, intuitively represented in the real world, but you can kind of like say these are features?
Yeah, I mean, so it's definitely going to be the case that that these features, they're just some nonlinear function of my input, and that could be anything. And it's up to this algorithm to decide what that should be. So sometimes it will turn out that they're interpretable. You can actually go dig in there and figure out what they're doing. But that doesn't have to be the case. Sometimes you can end up with weird situations where the algorithm has decided, I don't need this nonlinear function down here. And it'll just start passing through values of X. It'll just set W to the identity matrix and just pass X straight through if that's the optimal thing to do.
So if I, instead of H, I put in the principal components, would those work as well as?
Right, so that would be an instance, so getting a little off course, but that would be an instance of using an unsupervised learning algorithm to create features for you. So if I compute the principal components of my data, project my data onto those, you could think of that as like a new representation. Turns out not to be very useful because what you wind up doing is removing information. You're reducing the dimensionality, but not actually giving yourself more power. We can talk about that more later if you're interested.
I have a question. So do you necessarily need to pass those WXs through a sigmoid function?
No. I'll have a word to say about this in a little bit. So the sigmoid function that I've used here is partly just to make it look a little like logistic regression. You have the Russian dolls here, stacking them one inside the next. But also, this is how things were done 20 years ago. The model that you're seeing here is the kind of neural network you would have been working on in the 1980s, for example. And the sigmoid function there, because it gives you something like a probability, people think of this as like a spiking probability of a neuron. So with this very particular model, we call a sigmoid neural network, this is sort of thought to be a very sort of crude model of how neurons in the brain might do computation. So even though I kind of drew this as like a bunch of modules chained together, this is actually a neural network. So you'll often see in neural networks literature, when people give talks, you'll see them draw these big things. This is just a cartoon representation for the functions that I've been showing you. So for example, I have my x's down here, and each bubble represents just one element in the vector x. So all these bubbles here together represent the vector x that goes in. And then here's h. So these are the outputs of that module. And each of these is one element, one feature stored in h. And then f is going to take all those features, and that single value f, hopefully, when we feed it into our loss function, it's going to tell us that f is a good function. And all these lines here, so normally people call these bubbles neurons, in analogy to the brain. And all these lines here are the connections. They show you how each of these variables depends on the other variables in the system. So in particular, h1 depends on x1, x2, and so forth. And f depends on h1, h2, but it doesn't depend directly on x1, right? Because it's down nested inside another function. So this is just a cartoon for representing that function pictorially. And when we think about what is the neural network doing, we think of the computation as flowing upward through this system. So I put my image in down at the bottom, I stick that into these neurons, and then I'll figure out what the value of the h neurons is, and then from that I'll figure out what f is. And then just a sort of notational thing. Remember we have this matrix W that we multiplied by X. You can think of each element in W as representing one of these connections. In the brain, we would think of these as synapses, connections between neurons. So for example, the connection between H1 and X1 would be the first row in the first column of W. And the connection between H2 and X1 would be W21 and so on. So again, this is just sort of a pictorial representation to show you all the parameters and the dependencies in the functions we've been working with. So all these things are completely interchangeable. And in particular, it doesn't take too much creativity to figure out that if we can do one layer, we can do two layers. So for example, instead of just having H be computed from X and then feed that into our classifier, we're certainly welcome to just do it again. We can take H, compute some new values, H prime, and then feed those into the classifier and build a deep neural network with many different layers of computation. So this is now starting to look like something more like maybe you could imagine the brain doing. So the basic idea is that if I look for some function f that makes really good predictions, now f has a lot of power behind it. F can actually use several sequential stages of computation to make its decision. But the key thing here is that these things are not hardwired. I actually can tune W1, this big matrix that represents the first layer of computation. I can tune it to do whatever I want. And in particular, I'm going to try to figure out how to set it up so that when I take W2 times H, I get some new features that just happen to serve the right purposes so that F works well. It's very sort of purpose-driven. Whenever we try to find the best F, we're just going to tune all these weights to try to make the whole pipeline work as well as possible. And even though I showed you this as a picture, this is just a fancy way of saying that F now looks like this, which doesn't look nearly as cool. And likewise, I can play the same trick. I can just break it out into modules. You can think of this as a chain of 3 different boxes, all strung end to end. Does that all make sense to everybody?
If you keep on adding layers, what are the problems we face?
A whole bunch. So I'll tell you about a couple of really important ones in a minute. So, yeah, go ahead.
Conceptually, that neural network that you're in, how does this thing, what's the motivation behind this? Because this exactly more or less looks like a neural network.
Yes, so this is literally a neural network.
But why, I mean, but neural network's been around for, what's the motivation for this?
The motivation, like the original motivation for why we tried to build this, or why is it that it took so long to get it to work?
I guess both.
Why is it not popular? Neural networks still we are not able to use, right?
Right, so it turns out that the reason this did not work very well, in fact, the version that I'm telling you about does not work that well in practice. It used to look like there was some fundamental problem. I'll tell you what that problem was in a minute. It turns out that that problem goes away if you have the right bag of tricks. And I'll tell you what some of those are in a minute. But the basic motivation behind this, just mechanically, and this motivation has been around for a while, is that I have these several stages of computation available to me, and I want to find a way to train them, to learn them, so that I can make really complex decisions. So disregarding the fact that there are some things about this that are not going to work in the end, I'm going to tell you, assuming everything went well, how we can use the tools that we've already been talking about to actually train something that looks like this. So before we said the way that we were going to find the best F is to use gradient descent. We're going to compute the gradient of this objective function, and then we're going to update the parameters to make the objective function lower. We're going to keep doing it until we get to a minimum. So we can do the same thing here. Basically, the only thing that we've got to figure out is the gradient with respect to theta. That's the same as with logistic regression. That's how I'm going to train that very top layer for F. But I also have to figure out the gradient with respect to W. I've got to figure out what change do I want to make to W in order to make the features down at the bottom work better. So once we've done that, we can do the same thing as before. We can just update W based on its gradient. We can update theta based on its gradient, and away we go. So if you actually try to work this out by hand, it'll turn out that the gradient with respect to theta is the exact same thing. You don't have to worry about it. You can just compute it by hand with a scratch pad and pen. The tricky part comes when we try to figure out what is the gradient with respect to W, which you can do by hand for sure, but it will be pretty ugly by the time you're done. So the way that we do this is actually to use the chain rule. Who remembers at a functional level how the chain rule works? This is your differential calculus quiz for the day. So remember, in calculus, when you have a function that's sort of a composition, I have one function that I apply to my variable, and I apply another function to that, and I want to know what's the derivative of the function with respect to the variable on the inside. There's a rule called the chain rule for figuring that out. So you don't have to work out, you don't have to expand the whole thing and work it from first principles. You can sort of chain together a whole bunch of derivatives in order to get the derivative for the whole thing. So what I'm going to sort of show you is how to compute the gradients for this in a very similar way. But this is made a bit more complicated by the fact that h is a vector now. Right? There's more than one value here that's coming out of this box. And it also has several inputs. It has w, which are our parameters that we get to tune. And it also has a variable I'm going to call z, which could just be anything. It could be the outputs of some other neural network, or it could be my data. So just think of this little box here as a generic one of those little modules. I keep showing you these little boxes that I've been chaining together to make a big function. So just imagine taking one of those guys out and holding it in isolation. We think of the inputs to that thing as being z and w, and the outputs as being h. This is just like one sort of generic instance of those boxes. So the way to do this is let's just assume for the moment that someone tells us the gradient with respect to h. So some guy down further in the assembly line tells us the gradient with respect to h. Says if you could change h in the following way, I could give you a better objective value. The question then is, how can I use that information to figure out the gradient with respect to z so that I can tell the next guy in my assembly line what to do? How can I also figure out the gradient with respect to w that tells me how to make my function work better? So the way that we do this is to use the chain rule. And if you go back and look in your calculus book, you actually get a formula that looks just like this. So the gradient, or the derivative of my loss function, which is living out here, with respect to z, for example, is equal to the sum over all the derivatives with respect to the elements in h, multiplied by the derivatives of each element of h with respect to each element of z. So this looks like a pretty ugly function. Raise your hand if the Jacobian matrix, though, makes sense to you. Oh, okay. The number of takers is going way down. So if you go back to your differential calculus book and you look up Jacobian matrix, it's actually really easy. It's just a big grid of a whole bunch of derivatives, where each row is the set of derivatives of h, of all the h's with respect to one of the inputs, and then all the columns are the derivatives of one of the h's with respect to all of the inputs. It's just a big grid that has all the possible pairwise derivatives in it. So you can think of that as being the sort of analog to the derivative when you just have a single output. Yeah.
Actually, I find that if you drop all indices, the derivation of the propagation that we are doing is much easier.
That's right. So if you're very abusive of your notation, as is being pointed out, if you drop a lot of these indices, it turns out a lot of the rules you already know from calculus just kind of fall back out and you can reuse them. I'll kind of show you how that intuition works here. But if you use the Jacobian matrix, you go look up how to compute this. It turns out there's a really simple rule. You just take that matrix and you multiply it by the gradient with respect to h. So if someone gives you this gradient that tells you how to adjust h to get a better objective, your job in life is to figure out how to multiply this Jacobian against that value. And that'll give you the gradient with respect to this one. We call this back propagation. Because if someone is telling me the gradient with respect to my output, I can figure out what is the gradient with respect to my input, which is going to let me keep computing gradients all the way through this stack of functions. And likewise, you can use the exact same rule to figure out the gradient with respect to w. So this is pretty neat because all I have to do is figure out how to do this computation of take the gradient in my output and turn it into a gradient at the inputs, and I can just keep playing this game all the way back through the system. Does the basic intuition mostly make sense, even if you can't remember the Jacobian and such? Okay, good, good. All right, so this is kind of really neat because this is local. You don't have to know what's happening way down at the end of the assembly line near F at the final decision. And you don't have to know what's happening before you near your data and all the processing that's happening there. You've only got to know the gradient at your output, and you only have to produce the gradient at the input. And as a result, we can build this lookup table just like you did in high school. Once you have a table filled with all these derivatives for really simple functions, you can compute the gradient or the derivative with respect to almost anything because you can just chain them all together. So in practice, most of us have a mental lookup table of exactly this sort for all the functions that we keep jumping into our neural networks. So for example, whenever I have a layer that's linear, where my features are just w times z, I know, just memorized, that if you give me the gradient, which I'm going to call delta here, just to keep it small, all I got to do is do W transpose delta. Take my matrix and flip it, multiply it by my gradient, and that gives me the gradient with respect to z in here. And likewise, if I want to know the gradient with respect to w, so that I can update those parameters, it turns out that there's a nice little formula. I take delta, which is my gradient coming in, and I multiply it by z transpose. And that'll actually give me a matrix that I can use to update w. You can do the same thing for the sigmoid. So the sigmoid is just a scalar function, right? It takes in a whole bunch of elements and spits out this S-shaped curve function of all the elements. And likewise, this is the derivative of the sigmoid function with respect to all the elements. And we can just pile all these things up. If you want to do more complex things like the square root of wz squared, it's maybe not clear why you would like this, but you'll actually see this in a whole bunch of recent work. Don't be afraid when you see these crazy functions in a neural net. There's nothing special. You can just use this exact same trick. Compute the derivative with respect to z, it looks like this. And compute the derivative with respect to w, it actually looks like that. And once I've got this big table, I know that some of these look a little bit ugly, you can actually chain these things together. So, for example, let's take that network that we started with. It's just got 2 layers. The way that our algorithm is going to work is we're going to compute all the outputs. We're going to feed our data forward through the system and compute H, and then compute F. And then, if someone tells me, which I can compute by hand, what is the gradient of my loss function with respect to F, tells me how to change my output to get a better objective value, then I can use this backpropagation algorithm to get the gradient with respect to H, the gradient with respect to those features, and the gradient with respect to theta, which is the update I need to make to my classifier. And then I can run that backward and find the gradient with respect to W, which lets me update the layers below. So in practice, it's probably too much detail considering I see a lot of quizzical looks from the lookup table previously. So, basically, if you just take a few items from that table and you multiply them together, you can actually figure out that the gradient with respect to W can be computed this way. Yeah?
Are these gradients always shrinking as you backpropagate?
Yes, in practice. So they don't have to. So the question is actually about a phenomenon that I can tell a lot of you are aware of that has to do with why this algorithm fails in practice. But mathematically, this is what we want to accomplish. Right? We can compute this gradient that tells us how to update W to get a better objective. And we know how to keep propagating that backward to train as many layers as we want. So does that sort of sequence, that sort of rough outline of how we update these parameters make sense? Okay. Yeah?
Is it a one-time backpropagation, or?
Okay, so once you compute this gradient, so you have to run your data forward through, and then you have to run this backward pass to get these gradients. That allows you to make an update to your parameters. And then once you've done that, you now have basically a better neural network, and you do the whole thing again. Just like you do for logistic regression, you just keep doing it in a loop until you can't do any better. So this is actually the training procedure that I was just explaining. Basically what we do is go through and compute these gradients, and then all we're going to do is just keep updating our parameters by moving downhill with gradient descent in a loop. And sooner or later, this thing usually stops. But it turns out, historically, this algorithm has not worked that well. So everything that I just told you basically brings you up like into the 1980s. So this is backprop. This is how you would have trained a neural network many years ago. There are a whole bunch of problems with this, which you might be aware of already. So for example, this is a non-convex problem. Remember when I said at the beginning that we could always find the very best f? We could always find the choice of theta that was the best possible one because this function was bowl-shaped, right? We could always go downhill and end up at the very minimum value of our objective. That's no longer true because we stuck all these nonlinear functions into f, and now we're trying to optimize over all these things. It turns out that we're no longer guaranteed to find the best one. In fact, we might get stuck at some value that turns out to be a very bad choice. So that's pretty unfortunate. Convergence criteria is a big problem. How do I know I'm done? It could be, for example, that you see your objective function going down for a while, like your algorithm is doing really well, it's fitting the data better and better, and then it stops going down. You say, okay, it must be done, but it gives you terrible results. And if you had just run it for another week or something, it would start going down again. So all these strange phenomena can start happening to you because this is a very complex, ugly-looking optimization problem. So this is a really big problem. And the other one, which one of our audience was referring to earlier, is actually a classic problem called the vanishing gradient problem. So it turns out that if you implement the neural network that I described to you, and you try to compute the gradient, you will find out that as you go down the network further and further, the gradients actually go to 0. Even if you have total garbage parameters, your gradient will just say, I have no idea which way to update the parameters to do better. I don't know what change to make in these parameters to give you a better function. This is a very severe problem. And finally, it's really hard to diagnose and debug malfunctions. So now you have this big, ugly, nonlinear system. If it's not working, you can't just go look at the parameters and decide what's wrong. There could be millions of them, and they're very hard to interpret. So remember I said that these features didn't necessarily correspond to anything real? This makes it really tough to tell if something's working or something's not. Was there a question there? Yeah. Right, so why this happens is a little bit unclear in every case, but one thing that can happen to you, for example, with these sigmoid shaped nonlinear functions is if you think about what the gradient of those things looked like. Let's run back real quick. So here's the gradient. I didn't mention here, sorry, these little circles with dots, that's like element-wise multiplication. So not matrix multiplication, just multiplying corresponding elements of a vector together, in case that wasn't clear. Notice that the derivative with respect to z is the sigmoid times 1 minus the sigmoid. What happens if this thing is close to 1? Then this goes to 0. And what happens if it's close to 0? It goes to 0. So the problem is, if the output, if h, my feature value, is either 1 or 0, the derivatives with respect to the input go to 0. And yet 1 or 0 is kind of the regime we want it to be in. It's really sure that this pattern is there. So this is a real problem. So it's clear that if it had responded somewhere in the middle, like 1/2 or something, and you get a nice large gradient value, it tells you how to make an update. But once this thing goes to 0, now when you back propagate, right, once this gradient goes to 0, you're all done. You're just going to start propagating zeros back through your system. So this is a big practical problem, and that's one way that it can show. So it turns out that a whole bunch of things matter, and figuring out all the little things that matter is part of what has got us to this stage where we can make these things work much better. So for example, the choice of nonlinear function matters a lot. Don't use sigmoids. I'll start right now. If you go home and implement all this stuff, don't use a sigmoid function. It will make your life much more difficult. There are some reasons to like it, but it makes life much more difficult. The initialization of the parameters. You've got to pick a random guess to start with. And if you start them really large, for example, you put in really huge values for all your parameters, it's really easy to make all those sigmoids saturate, to drive them to 1 or 0, and now you're stuck. You can't optimize anymore, even though you just chose garbage parameters. So you can see how easily this gets out of hand. With something as apparently innocuous as just setting my parameters to big values to start with, could doom you for the rest of your optimization, that you can't actually make any progress from this random initialization. And finally, we've been talking about this gradient descent algorithm, which actually a lot of us are still using. It turns out there are actually parameters in the algorithm that you have to get right. So for example, setting the step size and how quickly the step size decreases is a problem. So if you go online and do a deep learning tutorial, you probably get to play with this optimizer and see how much fun it is to find the right step size value.
Where is the tutorial?
I can tell you at the end. There is actually links at the end of this, the slide deck that you guys will be able to pick up later. So just as an example, right? Yeah, go ahead. Oh, schedule is as a function of how many iterations I've done, how many times I've updated my parameters, how should I change the step size, the size of the next update. So in practice, it turns out some of these things work better if you make smaller and smaller updates as you go. But how small should they be, and how quickly should it decay? It's sort of a dark art. So there are theoretical choices of schedules that are supposed to work really great. But again, because this is a non-convex, ugly, nonlinear problem, it just turns out not to be very helpful. So said the sigmoid is really bad. This is one of those places where it looks like the deep learning story is kind of breaking down. We started out saying, well, we want to get rid of all these features, right? We don't want to engineer features anymore. But I've just told you that that picture of building this deep neural network so that we don't have to train features is sort of broken. Because we have to know, for example, that you don't use sigmoids. You've got to use some other function that might look like one of these. So for example, some seemingly silly change, like making your sigmoid go between -1 and +1 instead of 0 and 1, actually makes a huge difference. So seemingly innocent differences amongst neural network implementations could be the difference between completely useless systems and extremely useful systems. So one criticism, I think, of deep learning is that if you don't know which one of these things to pick, you're sort of back in the same universe, where you've just got to try a whole bunch of stuff and engineer a whole bunch of things to find something that works. But I think one of the cool empirical findings is that once someone figures out that one of these things works really well for one application, it tends to work pretty darn well for lots of other applications too. It seems to be quite generic prior knowledge that we can build into these systems. And if you want to do computer vision or audio or whatever, it very often turns out that if you find someone at a conference who says, hey, I changed my nonlinearity to this, and it works 3% better on my problem, you can go home and change it in your own neural net and actually do better. And that is exactly the kind of story for a function that looks like this. So a rectified linear unit seems like a trivial function, but now a whole bunch of us are doing this in our neural networks. And it actually does work better. Some questions?
So do we know what real neurons do?
I don't know what a real neuron is doing. So I think, in neuroscience, there's a lot of really amazing work trying to figure out the physics of the neurons. If we really understood those physics, maybe we could sort of reverse engineer the system. I think, roughly speaking, when there's a pattern that looks like whatever that neuron's turned to, the neuron starts spiking really quickly. When that pattern goes away, it decays and it turns off. And outside of that, I think you need to talk to experts. But the ones that I know will say that that model is completely wrong, and yet sort of one of the better ones that we have at this point. That the system is really complex. There's things like competition going on where if neurons around you turn on, they'll cause your neuron to turn off and so forth. So we have models of that sort of stuff, but it's a very complex system. Yeah?
Hi, I noticed that there are sharp turning point in your two of the cost functions.
Yep.
So I just wonder, when you compute the gradients?
When you compute the derivatives, yes. So very, very good. So stuff is always shuffled under the rug. This is not a differentiable function. So if you ever happen to have an output that is exactly 0, it's actually not clear what the gradient is there. Thankfully, in most situations, there's something called a subgradient. which generalizes this sort of theoretically that does exist there. But in practice, for one thing, you almost never end up with exactly 0. So that's nice. But even if you did, it turns out you can just pick any reasonable gradient there, like pick 0 or -1 or +1, and it basically does the right thing. Yeah?
So we started off with functions that saturate, that are limited, but then we have these functions.
Yeah, that's right. And that, it sounds like that might actually be a feature, not a bug in practice. So the question was that we started out with these functions that saturate, so that even if I put a really big value in, I can't get a big value back out. It sort of prevents my system from exploding. These guys here, it turns out, we'll often take this kink and we'll let it slide a little bit. We'll let the algorithm figure out what the threshold should be by putting some extra parameters in there. And when you're allowed to threshold, you can prevent things from blowing up. And if it turns out that that's the right thing to do, you kind of hope that your optimizer figures that out. But in practice, if your inputs aren't too big, that stuff doesn't necessarily have to happen. So anyway, this is a fairly low-level technical slide. You kind of don't need to know about this to understand what deep learning does. But if you go home and you try to do a tutorial, it's kind of nice to know that there are these nonlinear functions out there and that changing these things out might work better. But this is sort of one really classic example of how a seemingly simple change in the network can totally change your results. So for those who are asking about initialization, I'm not going to dig through this slide because this is pretty highly technical. So if you're going to go home and implement this, feel free to come back to this slide. But it turns out that people have come up with some pretty brilliant strategies for initializing those weights to values that they know will not blow up. So that if you set all your weights to random values that are just the right magnitude, then you can make sure that all of your neurons are very nicely behaved when you start it. Doesn't guarantee they'll be nicely behaved forever once you start optimizing, but at least get you started. So I'm going to jump over a bunch of these things. You guys can come back to this stuff. How many people here work on like computer vision problems? A few people. Okay. How many people work on audio? Text? It's like the Twitter crowd. But it's, I don't know, I'm kind of curious. Survey like interesting machine learning applications people are working on that are not audio, text, or vision. There's one back there. Yep. Oh, I'm curious what it is. What? Oh, recommendation systems.
Financial data.
Financial data. Okay. So the stuff that I'm going to talk about is particular to vision. So a lot of these slides were cooked up for a computer vision conference. But I think you'll be surprised. A lot of these ideas actually work great in other domains too. An example, for example, of this phenomenon is actually local connectivity. So let's take the example that I've been working with on computer vision applications. I want to take an image, put it into my neural network, and then at the top of my neural network, I want it to make a prediction about whether this is a cat. One thing that I could do is just take my entire image and hand that in as the inputs to my neural network, right? This whole image stretched out into a vector is X. Does that make sense? Unfortunately, if you try to do this, let's say that this image is like 1,000 by 1,000 pixels. Then that's 1,000,000 inputs. And that means that every neuron in your first layer has 1,000,000 connections to this image. So aside from the computational problems, it turns out that these things are actually really hard to train. You need a lot of data to estimate 1,000,000 parameters. So it would be really nice if we could just get rid of a lot of these. And in practice, it turns out that what you can do is just throw away huge fractions of the connections by saying that each neuron should just look at one little local region. And then maybe if I have some more neurons next door, they're going to look at some other region of the image. But having neurons that look at the whole image all at once turns out to not be very useful. In fact, if you actually just eat the expense and train these systems with all those connections, it turns out that they'll often learn little tiny edge filters and set everything else to 0. So the algorithms will often learn that all those connections are just not useful, and it will wind up learning some little edge filter or something. So if you work on audio, for example, you can use the same sort of trick. Don't let your neurons look at huge swaths of time and all of the frequencies. Instead, you can have a neuron looking at a little slice of time and maybe a small bin of frequencies or something like that. Same with any other application where you have a really large input. So in practice, the way that we think of this is that each neuron is looking at these little patches, and then each neuron is looking at all these regions staggered across the image. Yeah.
You described it as linearizing the specter out of this two-dimensional image.
Yeah.
Aren't you throwing something very important away? Because now you're talking about localization in 2 dimensions.
Yeah,
and
yeah.
You're talking about 1 dimension.
Right. So another way to think of this, so if Z is my image here, so this thing is a vector that is represented by Z. The other way to think of this structure here that I'm only connected to a little patch is that most of the elements in W are set to 0. I'm just constraining them to 0. Now the fact that this thing is a 2-dimensional image means that the set of non-zero values in W is going to have a weird sparsity pattern. It's going to be like a bunch of non-zeros. It's going to be 0 for a long time, and it's going to be a few non-zeros again, and 0 for a long time.
I guess what I'm trying to understand is that, yes, you're taking a subset, but that you've defined a certain notion of locality here for that subset. You could just as well say, throw out every other pixel that you're going to look at for this neuron.
Oh, that's right.
And so
yeah.
you've made an assumption about some kind
That's
of...
true. So the observation here, which is a good one, is that if I didn't tell you that this was an image, and I just gave you the vector, you would not know how to cut up this thing into 2-dimensional regions. So this is computer vision specific knowledge based on our understanding that what is going on way over on the right of the image, at least at the low level, is totally irrelevant to what is going on over at the left side of the image. Like whether there's a little edge over here doing something tends not to affect what's happening on the other side. And so it's okay to slice this up into little pieces and work on them separately. Yeah.
It might make more sense to some people, you know, how they have the visual pathway and the lateral shift and the LGN.
Oh,
vectors to show layers like that they're running like edges. And a lot of the vision systems like that they're running edges to show out layers to the abstraction. Like,
Yeah, so I actually, so we have a whole section in here on unsupervised deep learning. And maybe, so there's a whole bunch of stuff in here that I actually don't want to jump through because it's technical detail that if you want to implement these algorithms, you'll find it pretty useful. But that is sort of, it sounds like it's kind of getting off into the weeds. That if you don't work on computer vision, maybe this stuff isn't that useful or it doesn't make much sense. So are there other questions just about what we were just talking about? Like why it's handy to sometimes chop down the number of parameters and so on. Yeah.
The 0 weight can still float up and down.
Right. So as one description of this constraint, I'm saying that it's like setting a lot of elements to 0. But in practice, we just don't represent those things at all. You just you don't store them in memory. They're never allowed to become non-zero.
So it's safe to say then that there's a lot of redundancy that we'll find in some of these lower layers. So we're essentially learning the same features again.
Yes. In fact, funny you say that. One of the things I skipped over is this trick called weight time. So when we know that I'm going to tend to use edges on the right side of the image and the left side of the image, and I don't want to bother to relearn that all the time, what we do is we say, all these neurons that are looking at different pieces of the image, I'm going to require that they all have the exact same weights. So it's just a constraint I add into my optimization that says all the neurons over here, they got to have the same parameters as the neurons over here. Really straightforward constraint to just bake into your optimization system. So, good. So if you end up going back through this talk, you can go find all these different components, which are really just sort of examples of functions. Right? I showed you like sigma of wx. Right? This is some function that we invented that we thought might be able to represent interesting things. The fact that we sort of slash our parameters down so that our function can only depend on a certain subset of inputs, this is kind of a piece of prior knowledge that we found works well. And you can do all kinds of this stuff. You're welcome to just tinker like crazy with the format of these deep functions. And if someone invents a module like contrast normalization, which is it's just a little neural module that normalizes the brightness of whatever is coming in. And it's just some parameterized thing that we invented, and you can just drop it into your system and let the algorithm tune all the parameters. So all the things I've been describing are sort of little tweaks to the system. You don't have to think of them necessarily as sort of huge insights. Yeah?
Can't you just learn contact normalization out of the data?
Yeah, if you have a fancy enough neural network, you can, at least in principle. In practice, you need a function that is so deep to represent a lot of these things that it's easier to just pick a module that kind of looks like the thing you want to represent that might be useful and just put it in there. And so a huge part of getting deep learning algorithms to work is figuring out what is the order of these modules, how do you want to hook them together. You'll have some pretty complicated systems that have multiple branches and all kinds of crazy things going on. But it's really just been engineered for each application. So I mentioned earlier that we have these deep learning algorithms now that are state-of-the-art systems for recognizing objects and images. Pretty much the stuff that you could figure out from this talk up to this point is enough to build a state-of-the-art neural network. And in particular, this diagram here is just another cartoon depiction of neural networks like the ones I've been talking about with a particular set of weights. So for example, each of these little pyramids is one of those neurons hooked up to a little local region of the neurons below. You'll see it says max pooling down here. That's just a neuron that just takes the max of a whole bunch of inputs. So basically, the idea is that a max neuron will turn on whenever any of its inputs turn on. And if all the inputs are off, then the max neuron turns off. You can think of it like taking an ore of all the inputs. So it's another example of a function that we pick because it's able to represent sort of interesting behaviors that we think our system should have.
Big is that? Is it W? Third dimension?
Sorry, you mean these? Oh, so this is coming from sort of, so you think of each of these big blocks as being, instead of like a two-dimensional grid of neurons, think of it as being just a big three-dimensional grid of neurons. And in practice, I could just stretch all these things out into a vector for the purposes of doing my math. But when I go to do local connections, I want a neuron that just connects to a few inputs, I would connect them to three-dimensional blocks in this grid. So let's see. It turns out that if you implement this thing, so Alex Krzyzewski, Ilya Sutskever, and Just Hinton are the ones responsible for this particular network. They trained it on a couple of GPUs on the ImageNet challenge data set. So, if you've seen ImageNet, it's this cool online image database with millions of labeled images. And there's a challenge contest every year. And the challenge is to be able to predict which of 1,000 classes a particular image belongs to. Show your neural network an image, you've got to figure out which of 1,000 different classes that image is an instance of. So it turns out last year this was the top performer, actually by a huge margin, something like 10%, which is a vast, which is quite a gap in terms of these benchmarks. So these are some of the results. I showed you the leopard earlier at the beginning of the talk, but some of these are pretty interesting. Like this image down here, the real label was a cherry, but the neural network says this is a Dalmatian, which seems fair to me. So some of those are fun. This one is interesting. The top most likely label chosen by the neural network, the output of the classifier that was strongest, was agaric. Raise your hand if you know what an agaric is. Oh, we have someone who knows. Okay, I haven't had anyone who actually knew yet. So the label is a mushroom, and that was actually the second highest. I had to look up what agaric meant on Wikipedia, and that's the picture there.
Wow.
So it turns out, like, partly because my vocabulary apparently isn't big enough, this neural network can actually recognize some pretty non-trivial patterns and do it very competently. So this is a really cool result. And as I said at the beginning, this is a kind of problem that 5 years ago I did not think would be solved. It's still not completely solved, but we've made a huge amount of progress. And it's very much enabled by neural network that looks like this, built on the tools that I've been talking about, and huge data, fast computers.
There's another one, C-Sale, has another image set, and it also has
Oh, Label Me.
yeah, label.
Yeah, so there are a bunch of these databases out there where people have figured out that having a ton of labeled data is really valuable for doing science and building these kinds of classifiers. And that's a huge enabling technology. So anyway, this is a really cool application. Really shocking to me when I first saw it. Go ahead.
I saw in your previous slide the word convolutional.
Oh, yes.
I saw a slide earlier that sort of explained it.
That's a fancy word for wait time. So remember I talked about this trick in response to one of the questionnaires, that sometimes I know that the features at different parts of the image should probably be the same ones. And so I say that the parameters for my neurons over here should be constrained to be the same as the parameters over here. Now, if I take the case where I think of all these neurons densely packed looking at pieces of the image that are shifted just by 1 pixel, it turns out that the way to compute that very quickly is to think of taking my little filter and convolving it over my image to get all of my neuron outputs. So that's where this name comes from. So it turns out, you can shoehorn this basic framework, this basic sort of system into a whole bunch of different applications. So I went through the literature for the last year or two and found a couple that were pretty neat. So Dan Chirasan, his co-authors have done this cool thing. You can actually take slides from like a biopsy and train a neural network to predict where the boundaries of membranes are. You can take an image and label all the pixels and say, these are trees, this is sky, this is the ground, these are buildings, for example. And you can train a neural network to predict what you're seeing there, to segment a scene. Pierre Sermonnet has done some really great work, has built some pretty awesome pedestrian detectors. Give your neural network a whole bunch of examples of what a person looks like when they're standing up. Tell your neural network to look at each piece of the image and ask, is this a person? And you can make a pretty good pedestrian detector out of that. And another cool one, so this one's from University of Michigan. Actually, Hong-Lak Lee is one of the professors responsible for this, came out of our lab at Stanford. Using a neural network to look at an image like a coffee mug and decide for a particular location, for a particular region in the image, is this a good place to grab the coffee mug? This is it's not normally what we think of when we think of like machine learning problems, like recognition problems. But if you can get labeled data, I can get you an image and I can tell you whether my robot was able to grab it there, then I can actually decide for some new mug that I've never seen before, is it a good idea to grab at a particular location? Some pretty neat sort of unorthodox or unusual application of deep learning. I'm really excited about this stuff because I think a lot of these things, many years ago we might have said, it's a really hard decision-making problem. How do you go from pixels in an image to, is this a good place to grab a mug? That seems like a very bizarre kind of decision to try to make. I would have no idea how to build features for that by hand. It would not be obvious at all to me. And yet you can use a neural network. In fact, not even a very big one to make these kinds of decisions. So let's see, how are people feeling? Are people like kind of tired? Want to know more? More. All right.
Yeah.
Question.
Before we jump to unsupervised, are there any tricks you can use if we only have positive data that is specific? Are there specific tricks for deep learning if you only have positive data?
So that's sort of like a novelty detection kind of problem. So it's a one-class problem, basically.
Yeah, you want to figure out if something belongs to that class.
Right. So